Hello, everyone. My name is Ayaz Akram, and I'm a PhD student at the University of California, Davis. In this talk, I will present our work on the performance analysis of scientific computing workloads using general-purpose trusted execution environments. This work is a collaboration between the University of California, Davis and the Lawrence Berkeley National Lab. Here is a brief summary of our work. So scientific computing often involves computing on large data sets which are very sensitive. For example, biomedical data or data which belongs to some um, government agency. As a result, it becomes very important to secure these environments. So in this work, we tried to analyze if the general purpose trusted execution environments can be used to provide this security and what kind of performance implications they might have. So our results show that AMD's SEV generally shows very little performance degradation, but it requires some special configurations, which basically refer to the interleaved NUMA allocation. However, some of the workloads can still show performance overheads, mainly because of the virtualization, which is a requirement of the SEV's programming model as well. On the other hand, Intel's SGX is mostly inappropriate for scientific computing, mainly because it shows very high performance slowdowns. And secondly, also because the programming model of SGX requires modifications in the applications, which is hard to do for scientific computing applications because a lot of times they are dependent on a lot of third-party libraries. So first, I will talk about why secure HPC matters. So as I just explained that in HPC centers, often we are operating on very large and sensitive data sets. So as a result, there are two kinds of security threats we have to be careful about. These are external and internal threats. External threats refer to the threats from the other users who are sharing the HPC resources, and internal threats refer to the HPC system administrator itself or other entities that have more privilege than the user itself. So as a result, in HPC centers, often there is a trade-off that is made because of these security risks, because the HPC facilities, they don't want to have the liability to take the risk of hosting something sensitive. At the same time, the users sometimes are also not willing to operate in these environments where they are not sure about the security of their data. And finally, if there exists any secure environment, usually these environments are not very usable. For example, they might require some special configuration to connect to those environments, or the way the jobs are scheduled probably will be very different from the more traditional NSF based HPC facilities. So why there is a need for this work? To motivate about the need for this work, I will quickly refer to some of the related work. So there exists some work on the performance analysis of these trusted execution environments, but it's mostly focused on either cloud or general purpose computing environments. And there has not been any work on the HPC applications and the HPC environments. So another thing that I quickly want to talk about here is the distinction between HPC and the cloud computing. We argue that HPC is different from cloud computing in many ways, and that's why this work is important. And it's necessary to look at the use of these trusted execution environments from HPC's point of view. And the main factors that distinguish HPC from cloud computing are that the resources in HPC centers are usually allocated to a single user at a time. The jobs that are running there are very highly multi-threaded, and usually they are batched together, and that's how they're launched. And usually the data sets that these applications are operating on are very large. And they might also scale across multiple nodes, and usually they perform very limited types of I/O. So all these things make it very important for us to analyze how the trusted execution environments would behave in the context of HPC centers and workloads. So what are trusted execution environments? So trusted execution environments, they usually provide through some kind of hardware enforcement, isolation guarantees between different entities in a system. And they use some kind of cryptographic mean to verify that whenever you're executing something in a trusted execution environment, that's a valid execution. And finally, they don't have very significant usability challenges. In order to further explain what's a trusted execution environment, we can look at the cartoon on the left side of this slide, which shows a normal computing environment where you have some physical memory at the top, then you have a runtime or other more privileged software like operating system or a hypervisor, and then you have some applications running. Now, a trusted execution environment shown in the gray block here tries to isolate a sensitive application, its runtime or operating system, and the data that this application is operating on, which is in memory. It tries to isolate all of these components from rest of the components in the system. And the common examples of trusted execution environments are Intel's SGX, AMD's SCV, ARM's TrustZone, and some academic solutions like RISC-V-based Keystone. Now, how do these fit in our threat model? First, we'll look at what is our threat model. And in our threat model, we care about the user who's using the HPC resources. And we assume that anything else in the system, for example, the operating system, the system administrator, or if there is a hypervisor, when you're, let's say, running a virtual machine, or all the other users who are sharing the resources, they're all not trusted. At this point, we assume that the physical attacks and cache side channel or any kind of side channel attacks are not within scope. Physical attacks are not within scope because we assume that you might have other resources like cameras installed to provide protection against those kind of attacks. And the side channel attacks are not in scope because the data that is sensitive that these applications might be operating on is generally very large, and the bandwidth of these side channel attacks is generally very low. So we don't expect that much of that data can be leaked through these side channels. And in order to understand how to these fit in our threat model, you can look at the right side of this slide, where the gray box shows that how using a trusted execution environment, you can create a zone of trust between a data provider and a data scientist. And this can allow to keep this zone of trust isolated from all the other entities in the system, including the compute provider itself. So obviously, the important question now is that what is the performance implication of these trusted execution environments? And we'll try to answer that question. So here's a brief summary of what are the performance implications. First, SCV doesn't incur very significant performance degradation, but the default NUMA policy can still incur some high penalties. So we have to be careful there to use special NUMA configurations, that is interleaved NUMA allocation. Irregular workloads might still see some performance degradation, which is mainly because of virtualization. And SGX generally has very high performance overheads. So before going into our experiments and the results, I'll talk a little bit more about how do these two Ts that we have focused on differ, and what are the platforms we have used to perform our experiments. So first, SGX and SCV's programming model can be understood by these two block diagrams at the top of this figure. On the left side is SGX, which usually divides an application into two parts, trusted and untrusted. SCV on the right side provides security at the granularity of virtual machines. SGX provides integrity guarantees, while SCV does not. And integrity basically means that any part of your data that you want to make secure would not be overwritten by another entity in the system. In terms of the secure memory size, SGX has a very limited size of secure memory, while SCV allows the entire memory to be secure. SCV doesn't require application changes, but you have to run things in virtual machines, while SGX requires application changes. So in our experiments, we picked a variety of workloads. Some of them are traditional HPC workloads, like NAS parallel benchmarks. And we also picked more modern HPC workloads, like like GBM or BLAST-N, which is a genomics workload, and then some graph workloads as well, using a road network as an input graph. The hardware platforms we used in this work for SCV, there are 3 different platforms which cover a variety of number of cores, different NUMA nodes, and different memory sizes. For SGX, at the time of our experiments, there was no server platform that was available to run experiments with the support of SGX, so we had to rely on a desktop platform. Another important thing that I want to discuss here is the NUMA configuration. So NUMA basically refers to non-uniform memory access. And as you can see on the right side of this slide, AMD Naples platform has very non-uniform memory layout. So there are 4 different NUMA nodes here, which basically means that every core die will have a different access latency to any memory that is not local to it, that is not directly connected to it. On the other hand, on the left side, we have an AMD ROM platform, which is a platform with much more uniform memory layout. And we have a dual socket system that we're showing in this slide. But a single socket of this system actually constitutes a single NUMA node, because as you can see, all the core dies are equidistant from the DRAM modules, because they're at the same distance from the IO die. So because in our platform, we use 2 sockets, so it constitutes 2 nodes. But we have a third platform as well, which is APIX 7402B based, where we use only 1 socket of this system. So that will be only 1 node. So we have 4, 2, and 1 NUMA node systems. And this is important, as you will see in the next slides when we look at the results of our experiments. So now let's look at what are those special configurations I was talking about for SCV that are needed. And in order to understand that, we'll have to look at some of the performance results. So I'm going to next show the performance impact of SCV when you use NAS parallel benchmarks, specifically D class of the workloads on AMD Naples platform, which is a 4 NUMA node platform. And because SCV requires you to use a virtual machine, so we'll be testing 3 different configurations. The first one is just running things natively on the host platform without any kind of virtualization or any kind of secure environment enabled. And this is our baseline. So you can see that in terms of slowdown, everything is at as a unit bar. Our next configuration is just running things in virtualization. That is using QEMU. And in this case, you can see that the orange bars are a little bit higher than the blue bars. And the geometric mean slowdown is still not very significant. But there is some slowdown purely because of virtualization. And thirdly, we add QEMU plus SCV. So SCV is enabled as well. And the green bars now, you can see that they are much higher than the orange bars. So that means there is a significant slowdown that is visible once you run things with SCV enabled. Now, in order to understand where the slowdown is coming from, we can look at some other results. The first is comparison with what happens when you run things on AMD ROM, which is a 2 NUMA node platform. And if you look at the encircled bar here, the geometric mean slowdown of AMD Naples platform and AMD ROM platform, you can see that the slowdown, though it exists for AMD ROM, is smaller than the slowdown for AMD Naples. An interesting thing here is that AMD ROM is 2 NUMA nodes platform. So probably when you go to less number of NUMA nodes, the slowdown decreases. And why is that? Why does that happen? To understand that, we'll look at an application which is run using SCV. And that we'll look at how over time memory is allocated when that application is running. So first, let's just look at only QEMU. And we have not even enabled SCV. So as you can see, we have AMD Naples platform, which is 4 NUMA node platform. And over time, as the application demands some memory, there is some memory that is allocated on all these 4 NUMA nodes, and application executes normally. Now, when SCV is enabled, what is happening? As you can see that there is no memory allocated, or almost no memory allocated on 3 of the NUMA nodes. And most of the memory is allocated on just 1 NUMA node, which is NUMA 0. And why is that? So when you use SCV, you have to lock your memory using mlock syscall, and that mlock syscall is responsible for all this memory being allocated on a single NUMA node. Now, in order to understand why that lock is necessary, we have to look at how encryption happens in SCV. So the right side of the slide gives you an idea of that. So we have on-chip data in our caches, which is plain text. And then the memory encryption engine in the controller encrypts the data whenever it leaves the caches and goes to DRAM. But in order to encrypt the data, it uses 2 things. One is the key, which is a guest specific key, the virtual machine specific key. And the other thing is the physical address of the block itself. And why does SCV uses the physical address? That is because by using this physical address, SCV can make sure that it can provide protection against the ciphertext block move attacks. And now, because of that use of physical address, you have to make sure that you lock your memory in physical address space so that it doesn't get moved unknowingly to other locations that might then later on lead your data to be messed up. So because of that requirement of memory to be locked, when your virtual machine is running, you call the mlock syscall, which by default, using the NUMA first touch policy, just allocates all the memory in a single NUMA node, because it doesn't know that the application that you will be later running would actually like to be scattered across different NUMA nodes. So as a result, such applications, they will have performance slowdowns. And this also leads to underutilization of memory because you're allocating all your memory at once. Now, what happens when you run things with interleaved NUMA allocation? So as you can see here with QEMU, all your memory is allocated on all NUMA nodes equally. But this is still on-demand allocation. And just to be sure, this interleaved NUMA allocation here, there's nothing special being done. It's being done through already available Linux utilities like NUMA serial. And similarly, when you use SCV, again, if you explicitly interleave your memory across all NUMA nodes, this memory is, although it's not on-demand allocation, all of it is being allocated at once at the start of your virtual machine, but it's still allocated across all the NUMA nodes, which at least the NUMA sensitive workloads prefer. So they would still be able to use memory on different NUMA nodes. And as a result, hopefully they wouldn't get any slowdowns. To understand if, or to see if that is really happening, we can go back to our results. So this was the results that I showed earlier. Now let's see what happens if we just bring in this interleaved NUMA allocation policy as well. So as you can see in this figure, the hashed bars, they refer to the performance or the slowdown when you use interleaved allocation. And if you look at geometric mean slowdown, the green hashed bar is almost at 1, which means that with SCV, you almost don't see any overhead when you use interleaved allocation. So in summary, the finding says that SCV can be used for secure scientific computing without much performance degradation if you configure things correctly. Now, in order to understand what are the other reasons for the performance impact of SCV, we will look at some other workloads like graph workloads and some other HPC workloads. So first, let's look at the graph workloads. These are the workloads which are executed on an AMD Rome machine, which is a 128 core machine, and it's a 2 NUMA node machine. And again, we show the slowdown for 2 different kind of memory allocation policies for native QEMU and QEMU plus SCV systems. I want to bring your attention especially to this workload SSSP here, which you can see that even the orange bars, which refer to the QEMU itself, show much higher slowdown. And that doesn't go away even when you use interleaved allocation. Because the main reason for this slowdown is that there's a high thread contention in this workloads which leads to a lot of KVM exits, which are caused by the pause instructions in the workloads, because it's just spinning while waiting for other threads. So apart from this workload, there are other examples where the virtualization itself is the reason for slowdown. As an example, let's look at some other HPC workloads on AMD Naples platform, and I want you to especially look at Blast and workload. And what exactly is happening is that this workload is basically IO bound. It uses a very big database, which is around 250 gigabytes. And the test platform on which we ran this workload had much less than that as its main memory. And as a result, you have to do a lot of virtualized IO disk operations. And that was the main reason of the slowdown in this workload. So in summary, there are some workloads, some irregular workloads mainly, where you can see overheads mainly because of virtualization. But it is a requirement of the SCV's programming model, so there is no way to get away from it. Thirdly, SCV initialization is also slow and can also bring in some slowdowns because of, and these slowdowns can vary depending on the amount of memory your virtual machine is allocating. So as you increase the amount of memory, the slowdown numbers go to a higher number. So now finally, let's look at how does or why does Intel SGX is not appropriate for HPC. So here's some performance data on SGX. I have different workloads. And as you can see here, that the slowdown numbers are much higher compared to SEV here. I mean, as high as 126x. The geometric mean slowdowns are generally above 25x. To understand why do we see these slowdowns, we can look at enclave page cache faults. Enclave page cache is the amount of secure memory that is used by SGX. And it is limited in size, as I had talked about it earlier, around 128 megabyte in the test platform we used. An EPC fault basically refers to whenever your application is trying to access something which is outside of that EPC range. And as a result, it's like a normal fault, which is handled by the kernel driver. That handling becomes very slow. So you can see that the EPC faults per million instructions and the slowdown generally correlate with each other. And those faults are primary reason for the slowdown. But that's not the only reason. We also observed that another reason for the slowdown is the impact of the execution threads when you run things under SGX. In order to explain that, we can have a look at two figures in this slide, where on x-axis we have the number of execution threads, on y-axis is the speed up that we are observing. And the blue lines show when you run things normally without any secure execution, and the red bars or the red lines show when you run things under SGX. On the left side, you can see that for this workload, which has a high memory footprint, when you increase the number of threads with SGX, the speed up is almost nothing. On the right side, it's a workload which has almost no memory footprint or very small memory footprint. And in this case, both SGX or normal execution scale pretty normally when you increase the number of threads. So basically what is happening is that the SGX driver, which is a single threaded driver, mainly for high working set workloads, when they incur EPC faults, because those have to be handled by the driver, that driver becomes a bottleneck. And even if you're trying to use many threads for your application, you will not be able to take advantage of that. So as a result, with increased number of threads, you see an extra reason for slowdown for your workloads when you're running things under SGX. So in summary, it is inappropriate because of its slowdown. And the other thing is the programming model, which I haven't talked much about, but its programming model requires the applications to be heavily modified, which is not suitable for HPC. So in conclusion, or in the end, I will like to quickly talk about some of the future trends in trusted execution environments. So In future, it seems like there are some enhancements that have already been introduced to SEV. SEV-ES basically tries to encrypt the register state of a virtual machine as well. SEV-SNP is actually bringing integrity to SEV, but this integrity is different from the way integrity is done in SGX, which was using Merkle trees. In this case, it seems like it will be more scalable with SEV-SNP. Also, it seems like most of the Ts are actually following the SCV-like designs and moving towards more towards like virtual machine-based trusted execution environments. Intel has introduced MKTME, which is multi-key total memory encryption, which is much like SCV's encryption and tries to encrypt multiple pages using different keys. TDX by Intel, which stands for Trust Domain Extension, is basically Intel's way of providing security at the granularity of, like trustworthy virtual machines. ARM's confidential computer architecture has come up with something called ARM realms, which are basically secure containers, and this security is maintained through hardware guarantees. And usually these containers are opaque to the hypervisor operating system. So in summary, in this work, we looked at the applicability of trusted execution environments for high performance computing and found out that generally the performance implications of these Ts are not very high for AMD SCV, but require some special configurations. SGX, on the other hand, generally shows much higher performance slowdowns. So with this, I would like to conclude my talk. And I would also like to point out that I'm available on this email address shown in this slide if you have any questions related to this work. And thanks for listening.